How's everybody doing? Doing good? Happy to be here. I'm excited to do some more physics. Thank you for the enthusiasm. I appreciate it. So next week's your exam. On Thursday, I'm going to talk to you more specifically about the exam, give you some guidance as far as specifics to study. But for right now, just understand that the exam is going to be a lot like the classwork that you've seen as far as difficulty of problems. You're going to see a variety of questions that really probe your understanding of everything we've covered so far. So as far as preparing, the best thing you can do is make sure you understand all of the classwork that we've done. If you feel good about the classwork we've been doing, then you're on a good path forward. And again, I'll give you more specific guidance on Thursday as to what you should be doing over the week. Sound good? Any questions, comments, thoughts, concerns? Yes. It's on both days, Tuesdays and Thursdays. It's split into 2 days because I don't want to give you 6 questions to do in a 2-hour period. Spreading it out. This will help you not get burnt out mid-test. This will hopefully give you the best possible. This will help give you the best possible results. What's up?
Can we still go to LA before the test?
There will be LA sessions next week. Yes, will be LA sessions next week.
So for Tuesday, will I cover like week 1, week 2, Thursday, week 3, 4, or will it be like?
It's gonna be more based on topics. So Tuesday we're gonna cover more of like Coulomb's laws, circuit stuff. Thursday it's gonna be more of waves and optics. Again, I'll be more specific about it when it comes to Thursday.
For the LA sessions next week, do they count for this?
Exam 1. They count for exam 1 as well. So the counter restarts the week after the exam for exam 2. Sound good? Any other questions? Yes.
For the LA session, that's like your base grade. How many times you've gone for the exam, or?
Yeah, it will. So you can't get more than 100% on the exam, but it will add points to your exam up until the 100%.
Okay, so it's whatever you get on the exam, and then
Plus the number of LA sessions, up to maximum amount. Any other questions? Yes.
I don't know. Is the LA questions or LA sessions or week 5?
There are LA sessions during week 5. Next week's week 5, right? Yeah, there are LA sessions. Any other questions? All right, we're still covering new topics this week though. And today we're going to be talking about potential energy. But before we talk about potential energy, the necessary requisite information we need to talk about is this concept of work. Work.
Wow.
In the sense of physics, right? We're not talking about work, your day job. We're talking about work, making things happen in the physical world around us, right? And do we remember how to figure out work done by some force? Yes, pops up there. We remember what the physical definition of work is. Force times distance, kind of. So force times distance is under a specific case, right? This is true under a very specific case, and that specific case is that force is a constant under which it's undergoing work. We think about talking about moving a box across the floor and we're providing a constant 20 Newton force to get it moving across the floor, this will tell you how much work is being done by that 20 Newton force. But if you start varying the force, if the force is dependent on maybe position, then you can no longer use this. This is just the simplified version. There is a more generalized version, a version that uses calculus. Do we remember that version of how to calculate work from a force that varies with position? What's that? It's an integral. It's an integral. Do we remember what this integral looks like? What this
Integral of what?
integral f dots, depending on how you've seen it, f dot dr, dot product, right? Vector products. Now, f dot dr. I'm using this format. You might have seen like f dot dx or f dot dy. I'm going to use f dot dr because typically when we talk about positional forces in electrostatics, we're talking about Coulomb's law. Coulomb's law says what? That the force is equal to K
Times Q1.
times Q1 over R squared. Exactly. K Q1 Q2 over R squared. Yes. This force, is it dependent on position?
Yes.
How do we know?
R squared.
Yes, dependent on R squared. It's dependent on position. So we couldn't have used this initial work equation that we saw last semester. We have to use the more generalized version, the one that depends on our displacement, that depends on our non-constant force. So we take this force, and first thing we would ask is it a conservative force? A conservative force means that it's independent of path, it's independent of how we get somewhere. And it doesn't matter if you go from point A to point B near a charge. It doesn't matter what our route we take is. Right here, this just cares about what our distance is. Now there's more formal mathematical ways to prove this, but you can just take my word for this is a conservative force. Being a conservative force means that this work applies. And plugging this into the equation, work is equal to integral K Q1 Q2 over R squared dr. We have seen this before, right? We've seen this type of integral before. So what does this solve out to be? Many of us remember calculus. We got to dust off our calculus muscles a little bit here, right? How do we take an integral with a exponent?
Well, yeah, you can do what, the constant, right?
Yeah. Take out the constants, absolutely. K Q1 Q2. No over R squared.
And then we could put, yeah,
Integral 1 over R squared.
or R.
dr. Or we could say R to the -2, right? Really wants to put it in this other form, and maybe this
A little easier.
it's a little bit easier for us to recognize exactly, right? And now we just take the integral of an exponent. How do we do this?
No, you need the exponent in front and then you -1. Or.
As a
add one.
derivative, right? Taking the exponent
Oh, shoot,
-1, right? We add 1 to the exponent, and then we pull our new exponent down, right? So we're going to add 1 to here. What's -2 plus 1? -1. So we're going to have R to the -1, and we pull that -1 out front. What we end up with is negative K Q1 Q2 over R, right? This is the solution. This tells you how much work is done by this force that is moving an object. This Tells you your work done from point 1 to point 2, R1 to R2. I didn't give you the specific limits, didn't say from one point to one point, but just from 2. Sound good? Not too bad, right? So we can calculate the work done, and why is it that work is important? Why do we care about work? Why do we care about energy in general, right? Work is just an energy. You work out the units of work is going to be in joules, like every other energy. Why do we care about energy? What does it matter to us? What's special about energy? Can't be created or destroyed. In other words, energy is conserved, conservation of energy. This means that if we take all of our energies together, our kinetic energies plus our potential energies plus work done, that this all must be a constant. So if these are all of our initial energies before we start moving, that must equal our final kinetic energy plus our final potential energy. Must be true, has to be true. You count for all of the energy and it must be conserved all of the time. So if we know what the work done is, then we can calculate something about kinetic energy, and kinetic energy is the energy of what? Energy of movement, right? Kinetic energy, if you know the kinetic energy, you know how fast an object is moving. So if we let a particle exist, a charged particle exists near another charged particle, from our work done by this electric force, you can figure out how fast that particle is moving after it's moved some distance. Now, last semester, we didn't talk a lot about necessarily work being done. Instead, we phrased it as something different. We said this is going to be a potential energy, right? We phrase these potential energies, and these potential energies are what's important about it being a conservative force, because our potential energy for a conservative force, well, conservative forces are what give you potential energies. We define this as our potential energy is equal to negative work done. Sorry, I should put delta U. Should be more cognizant of that. Delta U. Change in potential energy is equal to work done to move it from point to point. So delta U suddenly becomes the negative of that KQ Q1, Q2 over R evaluated from one point to another, R1 to R2, R2 to R1, whatever final and initial position we have. So our delta U is the potential, is the work done between these two spots. We wanted to know what the exact potential energy is, just how much potential energy this thing has at some position U initial, perhaps, or U1, or U whatever subscript you want to represent. You can calculate potential energy, KQ1, Q2 over R. This tells you about the potential energy of a charged object near another charged object. All right. So now drawing out a picture. Hello. So drawing out a picture, what does this look like? Well, we might have two charged particles existing, right? And I'm going to start introducing this idea of mapping out things in coordinate systems, in our XY coordinate system. We say we have some charge. We have a 3 coulomb charge, right? No longer dealing with protons and electrons. You're saying we have a 3 coulomb charge right here at the origin. Plus whatever charge it is, just right there at the origin. Position 0, 0. And we put another charge at some position, maybe 2 centimeters, 3 centimeters, at this location, right? Wherever this charge is, maybe it's an X. We can calculate the potential energy that this object has, the potential for it to do work, potential for it to move. We can calculate the potential energy that this has due to just being in proximity to this. We call this U1. Right? We say it has some potential energy U1, dependent completely upon the distance R1. Right? Then we take this object and we let it go. What's going to happen? What you're going to attract. So we hold this one in place, and this negative charge is going to move directly towards this other charge. A little bit later, it's going to be at a different location.
Oh,
It's going to be moving. We're getting into dynamics here. Talked about forces for a while. A little bit later, it'll move directly towards it, straight line path. Some distance now separated by R2, some potential energy U2. Not band U2, potential energy U2. So we have two different potential energies, but what must be true is that energy must be conserved. So we say that our change in potential energy U is equal to our change in kinetic energy, or we could say initial energy is equal to final energy, both these identical statements. So you take this, you say, all right, change in potential energy is equal to change in kinetic energy. That means that we can figure out how much speed has been added to our particle by just letting it fall in. We can figure out information about what the speed is here. And that's the use of energy. Gives you a nice, easy way to calculate speed, no vectors required, right? U, potential energy, scalar value. Kinetic energy, scalar value. Instead of dealing with Coulomb's law, which gives us tons of vectors that we have to deal with, instead of dealing with Coulomb's law, we can do with scalars and figure out information about a particle's motion. That's why energy is a powerful thing to know. Are there any questions about this? Thoughts, comments, concerns? Yes.
Is it R squared under KQ1Q2 or just R?
no, that's the integral.
It's just R because we got it from the integral, right? So energy, Coulomb's law is R squared. We look up here at what we integrated KQQ over R squared. But after you integrate it, it gets rid of that squared, leaving us with this just divided by R.
And really, it's like kind of like
Was
a delta R, or no, huh?
It's not going to be delta R. Remember, these are inverses.
Well, that's what I'm saying, but it's gonna be minus R2.
Yeah.
Or
So
something, you know, it's like really that difference in the, that's what I meant.
yeah, but we have to be careful about that because what it is it's going to be the difference. So if we say delta U, I'm just going to draw it over here real quick because this is an important math note to make, right? We say what is delta U? Well, it's K Q1 Q2. I'm going to put over 1. And it's not the difference of what 1 over R1 minus R2. It's the difference of 1 over R1 minus 1 over R2. Right? Have to be careful with our algebra here. We cannot combine these
Okay,
just like that. If we wanted to combine these, it'd be like R1, R2 over, or R1 minus R2 over product, right?
okay.
So you have to be careful with your algebra. It's tempting to make that step. It's not a valid algebraic step.
Okay.
Take your algebra step by step. Make sure you guys are comfortable with it. Any other questions? Thoughts, comments, concerns? All right. Let's give you guys a little bit of work to do. Let me. This is the 13th, right?
Yeah.
I'm pretty sure that's right. You are. So this is your classwork for today. You're going to do a problem involving potential energy. It's a new problem for you guys to do. It's going to be figuring out information about final velocity based on this changing energy. Real quick, kinetic energy. How do we calculate kinetic energy?
1/2 MV squared.
Absolutely. 1/2 MV squared, perfect. Just to remind you guys from last semester. It also has you guys dealing with problems that utilize coordinate systems, uses your usual Cartesian coordinates, your x, y's. I want you guys to get comfortable with that. We're going to be using a lot of coordinate systems in this class. I'm not always going to be giving you pictures. We're going to have to be able to figure out where things are located based off of positional coordinates. And then you guys have a question involving refraction and speed of light. Remember, as material or as light travels through different materials, it's not always going to travel at that 3 × 10⁸ meters per second. As soon as light enters a material, it's going to slow down a little bit depending on that index of refraction. So things to take note of while you go throughout your work. If you have any questions, be sure to call over either myself or one of the 2 learning assistants. We good? Yeah. All right. 3, 2, 1, break. Oh. And for those of you that stick around towards the end, I will be going through 1 or 2 of these problems with you guys as a class.